are getting really good at reasoning, solving math problems, proving theorems, even coding like pros. But how they get so good is often a mystery. Big names like OpenAI and DeepSeek have shared impressive results, but their secret RL training recipes is still locked away. That's where DAPO comes in. This open source RL system finally reveals the key tricks that make large-scale LLM reinforcement learning actually work. At its core, DAPO introduces decoupled clipping and dynamic sampling, solving long-standing RL challenges like training instability, reward noise, and entropy collapse. It achieves state-of-the-art performance with half the training steps. Now let's dive in.
In reinforcement learning for LLMs, many top models, including those from OpenAI and DeepSeek, don't fully reveal their training techniques, so it's hard for others to reproduce or improve on them. Here, a new method called decoupled clip and dynamic sampling policy optimization, DAPO for short, is introduced. The team doesn't just propose a new method, they also release all their code, algorithms, and datasets so that anyone can build on this work. Look at the graph here showing how DAPO trains the QWN 2.532B base model. The model steadily improves, scoring 50 points on AIME 2024, while the older DeepSeek R10Q132B model plateaus and only reaches 47 points. Even better, DAPO gets there in half the training steps. The paper hints at 4 core techniques that make this approach work but doesn't detail them just yet. The main takeaway is that this isn't just about performance gains, it's also about making large-scale RL more transparent and accessible. Scaling up LLMs with reinforcement learning has become more complex. The big problem is that top methods from places like OpenAI and DeepSeek remain partly closed, so others can't replicate their results. This work sets out to fix that by introducing DAPO, a fully open-source RL framework designed specifically for large-scale training. Here, Q1 2.532B is tested, and a straightforward RL baseline scores only 30 on AIM, a big gap from DeepSeek's 47. Why is it so low? Traditional RL techniques struggle with entropy collapse, reward noise, and instability. DAPO addresses these issues with 4 key ingredients: increasing policy diversity, refining sampling strategies, improving loss functions, and shaping rewards in a meaningful way. To ground things, consider proximal policy optimization, PPO, a popular RL technique. It stabilizes training by limiting how much the model's policy can change on each update. The math describes how PPO clips updates to avoid big policy shifts, and how it uses weighted advantages from past rewards to guide learning. The central idea? Prevent huge jumps and keep training smooth and stable. Everything here, from code to dataset, gets released openly, so no one has to reverse engineer the secret sauce. It's about democratizing RL for LLMs and pushing research forward without hidden tricks. In large-scale RL, it's not enough to just throw in more data. Training stability is crucial. One common pitfall is entropy collapse, where a model repeatedly generates the same answers. That's why there's something called clip higher. Check the graphs here, showing how models trained with clip higher maintain higher entropy longer, meaning they produce more diverse outputs instead of getting stuck. Another focal point is how the model estimates advantage, how much better one decision is compared to another. Standard methods rely on a value function, but group relative policy optimization, GRPO, is different. Instead of assigning absolute scores, it compares responses within each training batch and normalizes them, guiding the model based on relative quality. This keeps training consistent and adaptable. GRPO also uses clipping to avoid huge policy shifts and includes a callback libler (KL) penalty to keep new responses close to the initial model. But for complex, long-form reasoning, clamping the model too tightly to its original behavior can limit performance. The authors here remove the KL penalty altogether to let the model explore more freely. That sets the stage for the changes introduced in DAPO. Next comes the tricky part of designing a good reward signal. Models can exploit naive reward schemes, also known as reward hacking. To avoid that, the researchers keep it simple. The model earns +1 for a correct answer and -1 for an incorrect one. That's it. This straightforward system has already worked well in fields like theorem proving, programming, and math competitions. Now we see how DAPO steps in. It refines policy optimization with decoupled clipping and dynamic sampling. ensuring stable training. The core idea is to limit dramatic updates while preventing the model from collapsing into repetitive loops. Mathematically, it controls how similar or different certain responses can be, forcing diversity. Look at how clip higher is used to stop entropy collapse. Traditional RL might apply a single clipping threshold, but here the approach is split into upper and lower bounds. If an action is rare, the model has more freedom to boost its probability, encouraging exploration. This method helps keep training flexible rather than locking the model into a rut of similar answers. Balancing the model's learning rate is critical. Push it too hard and things become erratic. Go too softly and progress crawls. That's where clipping strategies shine. Look at the left graph here. It shows that probabilities stabilize over time, thanks to clipping, allowing the model to learn steadily. Look at the right graph, which tracks how many responses reach perfect accuracy. If that rate climbs too fast, the model can stall. Why? Because there's no more room to improve if everything's already correct. Dynamic sampling solves this by removing samples that are always right or always wrong. Keeping the middle ground examples forces the model to focus on areas that really need learning. Mathematically, DAPO splits the clipping thresholds for different probability levels. Expanding the high clipping range helps rare tokens appear more often, preserving diversity. Meanwhile, a tight low clipping range ensures those rare tokens don't vanish completely. Together, these strategies stabilize RL and keep the model from repeating the same answers over and over. Now consider how each token in a response matters. If you treat the entire response as a single unit, you risk overshadowing the significance of individual tokens, especially in long answers. The left graph here shows how introducing token-level loss helps maintain entropy. That means the model doesn't produce chaotic or repetitive responses. Meanwhile, the right graph shows that response length remains steady, preventing the model from generating answers that are too short or too long. This is exactly why token-level policy gradient loss is introduced. Instead of evaluating entire responses as one block, each token gets its fair share of attention. That way, short yet insightful responses carry enough weight during training, and the model isn't driven to produce unnecessarily long or repetitive outputs. Finally, we see that if you cut responses off too aggressively to avoid overlong answers, you might introduce unwanted punishment and noise. It's called overlong reward shaping. Truncation strategies need careful design, so the model doesn't get blindsided by length caps that have nothing to do with correctness. Overlong responses can be a real headache. If a model's answer gets truncated, it often receives a penalty. But sometimes, a long response is valid. How do you handle that without confusing the model? Overlong filtering is the first fix. Instead of penalizing truncated answers, the model skips them during training. If you look at the left graph, accuracy goes up. The right graph shows that entropy also stays stable, which means the model doesn't become erratic. Still, you don't want endless rambling. Soft overlong punishment tackles that problem by giving a small penalty for slightly overlong answers and a harsher penalty for really lengthy ones. This keeps the model concise without punishing it too much if it needs a bit more space to reason properly. Meanwhile, the DAPO training loop involves generating responses, scoring them, and applying dynamic sampling to filter out unhelpful cases. By balancing reward shaping, filtering, and proper clipping, the model learns to produce answers that are both coherent and well-structured. Another challenge comes from handling mathematical data. Sometimes answers appear as formulas, expressions, or plain numbers. That leads to confusion when the model tries to interpret them. So the dataset here is cleaned and converted into a simpler format. For example, tricky expressions get turned into integers. That helps the model avoid mistakes caused by inconsistent input formats. The training uses AtomW, a well-known optimizer, with a batch size of 512. The model samples 16 responses per prompt for more variety. Clip higher is carefully tuned so the model explores enough, but remains stable. Overlong reward shaping also comes into play, setting maximum token lengths and applying a soft penalty when the model goes too far. Check out the results on AIM 2024, a 50% accuracy rate, beating earlier models like DeepSeek R10Q132B. Best of all, this was achieved with only half the training steps. It's not just about hitting a good score, it's about doing it efficiently. How much do these tweaks help? Look at Table 1 here. It breaks down how each technique raises the model's accuracy. Start with Vanilla Group Relative Policy Optimization, GRPO, and you get 30%. Not great. Overlong filtering helps by making training more stable. Clip higher prevents probability collapse by giving rare responses a fighting chance. Soft overlong punishment keeps the model from rambling without shutting it down too harshly. But dynamic sampling, DAPO's signature trick, provides the real boost. It cuts out the useless samples without slowing training, so even though you have fewer but more relevant samples, you actually learn faster. That's how the model hits 50%, surpassing DeepSeek's best. More data alone isn't the magic bullet. Ongoing monitoring of intermediate metrics is crucial to ensure the model doesn't memorize or collapse. Length, reward trends, and entropy all get tracked, helping the authors confirm the model is truly learning rather than just memorizing. Speaking of monitoring, Figure 7 here tracks 4 metrics that reveal training stability. First, mean response length grows over time, meaning the model is gradually learning to offer more detailed reasoning steps. That's typically a good sign, suggesting deeper analysis rather than shallow answers. At the same time, rewards go up and then level off, indicating the model is steadily improving. Entropy serves as another window into the model's behavior. If entropy gets too low, the model is overconfident and doesn't explore enough. If it's too high, the model is scattered and incoherent. What we see is a slight dip in entropy, indicating the model gains confidence, and then a small rise, meaning it recovers some diversity without going off track. Meanwhile, the mean probability heads downward, suggesting the model is spreading out its bets rather than zeroing in on just 1 or 2 responses. What does that mean for the model's reasoning? Over time, it starts revisiting earlier steps, backtracking, and refining its logic. Early versions might not do this. It's a sign that RL is shaping how the model thinks, not just which final answers it produces. Finally, there's a fascinating example of how the model's reasoning evolves. Check out Table 2. Early in training, the model automatically applies formulas to get the volume of a tetrahedron. That might work sometimes, but it's not always correct. As training continues, the model slows down and actually rethinks the geometry. It reflects on whether the formula applies to the specific shape, showing more structured problem solving. The main insight is that RL doesn't just optimize numbers, it nudges the model toward richer reasoning behaviors. This is critical for real-world tasks where a model might need to rethink, verify, and refine its own outputs. This all wraps up with the message that every part of this system, DAPO, the dataset, and the full training pipeline, is open source. Anyone can see how it's built and tweak it. The core techniques of decoupled clip and dynamic sampling policy optimization demonstrate how to scale RL while keeping it stable and efficient, boosting the model's problem-solving abilities without excessive computational overhead. Thanks for joining us today. Happy exploring!